Hello and welcome back. In this video, we are going to look at the linear regression implementations in uh, TensorFlow, Python, Kotlin, Keras, and scikit-learn. So I'm trying to make this special video. Hopefully, it will help you sort of look at the comparison between the code to sort of do the same thing, which is linear regression in this case. So on the screen I've put up all the code, uh, but the font size it gets too small, so I'm going to move some of these down, and we'll look at first first we'll look at the TensorFlow, which is this one. Then we have Python, which is the cent in the middle. Then we have Kotlin on the right hand side, and after we are done with those three, I'll start explaining Keras and scikit-learn, which is down here in the bottom. So to get started, in the first, what we have here in TensorFlow, we of course we import the libraries TensorFlow as TF, NumPy, and then I've imported matplotlib for plotting. We set the random seed to 42, and I'm using both of these. Then to create the data set, here I'm using NumPy arrays, and it's the same set of data that is used in all of the codes uh, that sort of are attached to Python. In here, in Python, we have the same X and Y. Likewise, in Keras, we again down here in the bottom, if you can see the code, I'm using the same values for X and Y, as you can see. So it's these are the same values. Likewise, in the case of scikit-learn, again, we are using the same values for X and Y. All right, I'll try to move these windows around so that we can look at the code. All right, okay. Next, when we look at, let me move this a little up. In case of Kotlin, the way the code is completely different than the others. Here I'm importing the java.util.random library, and in Kotlin the code is written uh, inside of this main function, as you can see, which goes all the way up to here. And if you are new to Kotlin, you might see this comparison will help you sort of get into Kotlin programming based on the syntax that you may already know in Python. So to set the random seed in Kotlin, this is the way to do it, where we need to specify the variable. So the value, so in this I'm saying it as value, because that value is not going to be changed. If we say var, then we can change the value of that on that variable that we have. So this is again set to 42, and we are using the random from Java that is initialized here. And then to create the values for X and Y, again the same setup. We get the values from 1 through 100, and that is for the X, and then we get the same values for similar values for the Y. And here we have the normal random np.random.normal directly. We can get that here. We need to use random.next Gaussian. And so thus in all of these 5 cases, we have created the data set with values for X and Y. Next is to split the data set into train and test set. Of course, there are different ways to do this. In this case, in the first code with the TensorFlow, what I'm doing is simply taking 80% of the data, putting it in the train, and the rest of it in the test set. So this is directly based off of the index. In case of Python here, I mean, we could use the same thing here, and that's I think that's exactly what I've done. Likewise, in this down below here for the Keras, I'm using the train test split, which is again from scikit-learn. So borrowed it from there, and this is test size we have specified here as 0.2. So 80% goes into the train set, and of course in scikit-learn then the same thing we have here, where the test size is zero point 0.2, so 20% rest of it goes in the test set. In case of Kotlin, to split the data set, the syntax is slightly different. First, I'm specifying train size and specifying what size, uh, how many number of records would go in that, and then using dot take to pick first those many records and put them in xtrain, and same thing with the y. Next, whatever values we have taken in the train set, whatever remains after that will come in here for the x test and y test when we use dot drop. So the difference in Kotlin is the code and syntax is completely different. I'm sure there are other ways to do the same split in train and test set, but this is just one of the examples. Next, once we have the train and test set ready, what we need to do is to get started with the regression part. We need the bias term to be created, and to do that, I'll put all of the lines along the screen so that you can see all of them. All right. So in case of the Python, this is what I have for the X train and X test. The bias term that we are adding to the X train is in this line of code, where we have the array of np.ones, and then we have the X train that is the original. So we are adding one constant, and this is the same setup that we have down here in Keras, uh, where we are adding the bias term, and again the same thing here in the scikit-learn as well as here in the Python. In case of the Kotlin, what we have is we are using dot map. And what dot map does is, and in front of dot map, we have this sort of a lambda function. What that does is it is creating a list of the value in xtrain and putting one in front of it. So so that's another way the bias is being added. Next, we have the learning rate, number of iterations that are set. So we have learning rate at 0.01, 1000 iterations, and I've tried to keep the same learning rate and iterations in all the cases. So let's see in, oh, right. So here I have the same thing. And again, in Kotlin, we have the same thing, as you can see. We also have the size of variable defined, which is m, that has sort of the number of rows. The variable m that we have defined here, I think we are going to use that in this Python code where we calculate the gradients. But in TensorFlow, I think that is not going to get used. Likewise, we'll use the value for m here in Kotlin as well. So m is defined regardless in all of these, except for Keras and scikit-learn, where we do not need that. After that, for the gradient descent step, here we have the for loop, as you can see, and we have the same type of for loop here in Python, and we have the same sort of for loop here in Kotlin. Okay. Now the difference between the way for loop is written in Python and Kotlin is, as you can see it here on the screen, in Python we are saying for iteration in range n underscore iterations. In Kotlin we are writing for, and then inside of parentheses we are specifying the variable which is iteration in, so that is the same. But instead of using range, we simply specify the range here by using the comparison operator. So 0 less than equal to until less than equal to n iterations. So that is saying is that proceed until you reach the value that's in n iterations, which is specified up above, which is 1000. And in case of TensorFlow, the gradient tape is available, which sort of records each of the calculations on the tape that we can use later on to later on down here. So with tf.gradient tape as tape, we are calculating the predicted value of y and using tf.mat multiply, and inside of that we have the x train underscore b, and then we have the value for theta. So that's sort of doing the dot product there, and as soon as we calculate the value of y pred, we calculate the error by subtracting the predicted value from the actual value, and then use the error to calculate the loss. And for that, we are using tf.reduce underscore mean. In case of Python, what we have is similar setup, except we are doing the dot product explicitly, as you see here, x underscore train underscore b dot theta, and we get the value of y pred. We subtract that value from the actual train value to get the error, and then for calculating the gradient, we are directly typing out the formula that we have for in case of linear regression. After you take the partial derivative, this is what relation that we get, and in that what we have is -2 divided by m into x train b, a transpose of that, dot with error. So we are dotting the values in x train b with the errors to get the gradients. And once we have the gradients, we then multiply them with the learning rate and subtract it from the theta to update the theta. Likewise, here, once we have the gradient, once we have the loss calculated, we use that to update the gradients in TensorFlow by using tape.gradient. So this here it does that all automatically. Here we are doing it sort of manually. Now, interestingly, in Kotlin, we can do the same thing. Just the syntax is slightly different. We have defined the value gradients is equal to and list size 2, and inside here we have a lambda function which again has the same formula that we use to calculate the gradient in Python, uh, except that when we are uh, multiplying with the error, the way this is written is different. We are using the dot zip to compute the product of error and xtrain b, and here inside of zip we have another lambda function that shows the actual multiplication. Once the multiplication is done, we are then going ahead and getting the sum of that. Once we have that, we then proceed to updating the theta. As you can see, again we are using .zip to uh, to use the values of theta and gradient for performing the updates to theta using this lambda function, where we are multiplying the gradient with the learning rate and then subtracting that from the theta to get our new value of theta. That then goes back up and updates in this relation where the y-pred is calculated, and then this loop will go on over several times until it converges. In case of Keras, as you can see here, because these methods have everything inbuilt, we do not see that calculated explicitly. What we have instead is simply building the model. So keras.sequential layers.input layer tape, and here we specify the xtrain that we have created above, and then we have our final dense layer with one node, and it'll do, and again this has normal seed set to 42. And finally, to compile the model, here we have model.compile, and we are using the SGD optimizer with a learning rate of 0.01, the same that we have used above. And the loss function is mean squared error, and that's what we are using in other cases as well. I'll talk about that in just a minute. And finally, we simply fit the model to the trained data set. Epochs is 1000, just as we have number of iterations in other cases. So that's how we would go ahead and performing the fit in Keras. Now in scikit-learn, in this case, I'm using SGD regressor, again with maximum number of iterations as 1000, and the learning rate as 0.01. Similar to Keras, we can do the model.fit on the train data set, and once the model is done, we can perform the predictions. But before we get there, let's go back up now to the code that we have in TensorFlow. So this iterations would go on. So we have the gradients, it'll update, and this is just to print the loss after each iteration. And again, this is the theta that we have that is getting updated. So here we explicitly said theta is equal to theta minus learning rate into gradients. Here we are doing theta dot assign underscore sub, which has learning rate multiplied by the gradients. So once we have in TensorFlow, once we have the theta, then we can use the final value of theta to calculate the uh, predicted values. So here we have the predictions for both train and test by simply uh, multiplying the the x values, that is the feature values, with the theta, and so we get those. And finally, to calculate the mean squared error, we are using tf.reduce_mean, tf.square, and here we have the difference between the actual value and the predicted value. In case of Python, we once we have the optimized values of theta, what we are doing is we are multiplying the x-test values with the theta, dotting them with theta to get the predicted values, and then to calculate the MAC, we simply subtract them, take the mean, and square them. So that gets us the MAC values. In case of Keras, in case of Keras, I think here I've used the same same method to manually do the calculation for calculating the MAC. In case of scikit-learn, we can use the function mean squared error, and to that we just simply input the values of y-test and y-pred to calculate the MAC. In case of Kotlin, uh, the same setup works for calculating the values of predicted values both for train and test set. We are using dot map. So all we are doing is taking the values of the features, be it x train or x test, and then using dot map. So similar to dot apply that we have in Python, and using this lambda function. So what essentially we are doing here is dot product. We are multiplying the value in x train, which is denoted here by the IT, and then multiplying that by corresponding value of theta. Once we have the value predicted values, we can calculate the MAC values on the test set by again using .zip. So we have ytest.zip, ytest-pred, and inside of this lambda function, we calculate the difference between the actual value and the predicted value, then get the sum of that. Get the raise it to a power of 2, and then get the average. So that's how we can calculate the mean squared error in Kotlin. And finally, here in Kotlin, we are printing the value for theta as well as the MAC. And so that's the way we would do it, and simply putting a $sign before the variable that we would like its value to appear here. In case of Python 3, we have put the letter F in front of the string, and so we can directly then put the variable name here in the curly braces. In case of this again is all Python, so everything stays the same except to convert the tensor into NumPy. I've multiplied, sort of dotted that with NumPy open close parentheses so that we can see it in NumPy array format. In Keras, as we can see here, we can get the weights by typing model.layers and square bracket 0 dot get weights and open close parentheses square bracket 0 dot flatten, and again we can print the weights, which would be the coefficients, and then we can print the MAC. The same setup is as we see here for the print, except for weights. We can directly get the weights from the model that we have fit in scikit-learn by typing .coef underscore. So as you can see, to do the same sort of uh, uh, fit to the data set, the lines of code that we need to write in, let's say, scikit-learn is much less as compared to, let's say, if we were trying to do it from scratch in Python, or if you were to do it in Kotlin. But I think this is a nice exercise to learn how to write code in different sort of platforms or different frameworks or different programming languages, and get a handle on sort of the syntax and also the concept of how these things work. So let's go ahead and run the code one by one. So I'm going to first run this code in TensorFlow, and let's see what output we get. I've already run that, so I'll just run this again. Here is the output. So we have the scatter plot for the y-test and pred, and you can see that's the scatter plot. We have a MAC of 0.97, and these are the coefficients we have for the theta 4 and 4.2 and 2.7. Let's run this code in PyCharm. I have this PyCharm IDE open, so I'll just go ahead and run this. And down below, we should see the code. Sorry, we should see the output here. And as you can see, the MAC is 0.96, pretty close to what we got in TensorFlow. And the coefficients are 4.1 and 2.7. Again, pretty close to what we had in the TensorFlow output. Next, let's run the code for Kotlin. And in Kotlin, again, the output that we see is a bit different. And for the MAC is a bit higher, 1.68, but the coefficients are pretty close, 4.4 and 2.8. Now, let's run the code that we have here in Keras and see what output we get. Sorry about that. Let's minimize this. And in here, I think the code is still running. Let me this part as well. So after that, we will go ahead and run the code for scikit-learn. Or I could actually go ahead and run this simultaneously. So run that, and so this was fast. We have MEC of 0.63, which is the lowest among all of these that we have seen so far. And the theta is different. Instead of 4, we have 2.18 and 2.57. And maybe that's why the MEC is lower as well. And in case of Keras, we have the similar value as scikit-learn. So this is also lower. This is 0.65, and but the values for theta are 4.13 and 2.79. So those are the sort of variations that we see in all of these outputs. So I hope this comparative video to do linear regression and gradient descent, you found this interesting and helpful. If you like this video, please let me know in the comment section below. And if you'd like to see similar comparative coding videos, I'd like to hear from you. And maybe if there is a lot of interest, I'll create a new series for this where we have several types of code going in parallel for accomplishing a particular task. Okay. Thank you for your time, and I hope to see you all in the next video. Please like, share, and subscribe. It means a lot to me. It sort of keeps me motivated to create more content for you all. Thank you.